talking about today is joint work with Parkman Peterson. So what I'll be talking about is exclusively about quadratic polynomials. Of course, you can talk about germs, but this is the framework of today's talk. So let me remind you of some basic facts. So I'll be talking about quadratic polynomials with a different fixed point at the origin, which means that the derivative at the origin is a rotation by some angle theta, called the rotation number. We call this quadratic mass linearizable near that fixed point if you can find a change of coordinates in which the mass looks like a rotation, local change of coordinates. And it's easy to see that in this case the rotation number must be irrational, and the maximal linearization domain around the fixed point is an open simply connected domain which is called the Siegel disk of the polynomial. So the action on this topological disk is conjugate to rigid rotation by angle theta. So as it's well known, when you consider this problem, number theory arises naturally. So there are certain classes of irrational numbers that turn out to be important in this theory, and I would like to remind you of these, some of these. So if you expand your irrational number as a continuous fraction expansion with integers a1, a2, a3, and so on, and then you truncate it at some point to form the rational convergence. I'm not sure if you see this. Then these rational convergence converge to your irrational number at least exponentially fast, classical. Now, we call theta diapantin of some order bigger than or equal to 2 if its distance to any rational number is bigger than a constant times the denominator to the power constant divided by the denominator to the power 2, which means that it's badly approximated by rational. Equivalently, if you take a look at the sequence of denominators of the rational convergence, the n plus first term is dominated by the appropriate power of the nth term. The appropriate power turns out to be nu minus 1. And then you form the class of all diapantin numbers with various nus, various orders. We call it D. This is the union of all of these classes. And it follows from this condition that the class of all diapantin numbers is exactly the class of irrationals for which the denominators, the n plus first term, is dominated by some power of the nth term. Now the class of diapantins of order 2 turns out to be another important class. It's D2, which is called bounded type. It's easy to see from this condition and the relation between qn's and these numbers an, that the number is in D2 you can only if this sequence of integers that you get when you expand this irrational number as a continuous fraction is bounded. So that's why it's called bounded type. Sometimes constant. And then we have the class of Bruno numbers. So this is the class B. The number is of Bruno type if the series converges. Logarithm of n plus first term divided by the nth term. So for the series converges, it somehow means that n plus first term cannot be way bigger than the nth term. Now we have this series of proper inclusions. Bounded type is contained in any diapantin class of order nu. Nu is bigger than 2. This is properly contained in the class of all diapantin numbers. And this class D is properly contained in D. And it's an easy exercise to see that this is full measure. Therefore, Bruno type is typical. So almost every irrational number is of diaphantin type or therefore Bruno type. So the reason why these classes are important is because of the so-called linearization problem. So we would like to know, as I said, we can talk about the general problem of linearizing germ, but let me stick to this special case, which already shows most of the characteristic difficulties of the problem in general. So this is the question we ask: when is an indifferent fixed point for this quadratic map linearizable? This is the so-called classical problem known as the center problem. So this theorem is really a theorem of Yoko's, but it's built up on previous work by Siegel and Bruno, that Bruno condition, at least for the quadratic map, is optimal for the linearization problem. So Siegel proved in 42 that every germ of diaphantin type is linearizable, and then Bruno extended that result to flotation numbers of Bruno type, and then it was Yoko's who proved that a non-Bruno quadratic polynomial is non-linearizable, and therefore Bruno condition is optimal. So this theorem, in some sense, at least in the quadratic case, finishes the linearization problem. So there is nothing else to ask because this condition is optimal, but it gives a little information as to what the global picture of dynamics of this polynomial looks like. And the problem, whenever you have a Siegel disk, because of recurrence of the critical points and the lack of so-called hyperbolicity, it turns out that the dynamics is difficult to understand. So at least the first approximation, we would like to, whenever you have a Siegel disk, we would like to answer these three questions. As I see it, some other people might be interested in some other features. So we want to know what we can say about the boundary of that linearization domain. In other words, how tame or wide the continuum can it be? For example, there is this conjecture of UID and Sullivan that at least for rational maps, this boundary is over the Jordan curve. And next, we want to know, suppose that we can show this boundary is the Jordan curve. So the dynamics on the boundary is well known as just rotation. So what can be said about the metric properties of this boundary? Is it a quasi-circle in the sense of L force? Possibly compute or estimate the Hunsdorf dimension of the boundary and so on and so forth. So the last question is, what prevents that polynomial from being linearizable in a slightly larger domain? What happens on the boundary that prevents us from extending that Siegel disk a little further? This question is raised by like Michel Harman. He had this theorem that at least for the quadratic case, when the rotation number is diaphantic, there must be a critical point. The critical point of the quadratic map must be on the boundary, and that is the obstruction. But later, Harman himself found some examples where the critical point is off the boundary. The entire orbit of the critical point is off the boundary, and therefore in those cases something much more complicated must happen. And that has partially been explained by the theory of hedgehogs of Perez-Markov, although none of these problems is fully settled yet. So let me, perhaps for non-experts, it's easier to look at this picture, analyze this picture. So this is the set of all theta in the unit interval or circle. And for rationals, pretty much everything is known as far as the dynamics and the topology of the Julia set is concerned. So when it comes to, I've divided this space into Bruno and non-Bruno. So in the Bruno category, we have bounded type and in this case, this Siegel bit, the quadratic polynomials with irrationally indifferent fixed points of bounded type are well understood. We can show that the boundary of the Siegel bit is a quasi-circle, and the Julia set is locally connected. The Julia set is locally connected, has measure 0. It has Hausdorff dimension less than 2, in fact. The boundary has Hausdorff dimension bigger than 1, but contains a critical point. If your rotation number is, say, golden mean, then the boundary is self-similar near the critical point. And a lot of things. This object has been the subject of a lot of studies in recent years, so we can say that the bounded type case is pretty much well known. But the problem is this is a very thin class in this space of Bruno numbers. So there are some examples of Bruno and non-Diophantine for which we know that the critical point, this is like Hermann type example, so you have a Siegel bit, and perhaps the boundary is nice, but you have a lot of indentations sticking out, so the Julia set is not locally connected. It has a horrible topology. So we knew that such examples exist, but still, this case is far from being totally understood. Of course, this Bruno and non-Diophantine is measure 0, but still very important to understand. And then you have the tremor type, which is non-Bruno but irrational, which is even worse. The Julia set is non-locally connected, and very little is known in this case. It's non-linearizable, of course, but one would like to understand what's happening in this Julia set. But still, a big chunk of this thing is missing, which is full measure. I'm cheating a little because you can replace this Diophantine with the class H, the so-called H, which is the optimal class for linearizing analytic diffeomorphisms, but for all practical purposes, this is not a serious cheating. You can assume the advantage. Well, here is the big missing part. We would like to know that when the arithmetic of theta is relatively tame, and this class is full measure, what's happening to the Julia set? So this corresponds to a full measure set of angles, full one-dimensional measure of parameters on the boundary of hyperbolic components in the manifold set. So this problem is very difficult, and we couldn't solve it. So we found another problem which was a little easier, and we still couldn't solve that. But then we tried to somehow play around with the arithmetic properties of rotation number to be able to get some information out of it. So this is the theorem that proves So this is the theorem. So we introduce a new class of irrational numbers, set of all irrational numbers, theta. When you express them in continuous fractions, you get the sequence an of integers. Suppose that this sequence is allowed to go to infinity in an exponential way in the square root of n. So this sequence is dominated, it's assumed to be dominated by an exponential function in the square root of n. So it follows from, say, a theorem of Pynchon in continuous fractions that this set of all angles of this type is full measure. It's easy to see that this is a subclass of Diophantine but it's full measure, and that's what makes the result interesting, because this is a large class of rotation numbers. And the theorem is, whenever you choose your rotation number in this class, the Julia set is locally connected and has measure 0, so it's as nice as you could possibly ask for. And in particular, the boundary of the Siegel disk is the Jordan curve, which contains the critical point. So this is perhaps the best we could ask for, because we can totally understand the topology of the Julia set and the dynamics of the polynomial on it.
Remind us the relationship between the boundary of the Siegel disk and the Julia set.
Well, it's a subset of the Julia set, so we have this piece of theta. Here, and then you define the filled Julia set as the union of bounded orbits. And then the Julia set is the topological boundary of the filled Julia set. So this is compact, non-empty, of course, compact, and full, in the sense that its complement is connected. This is the topological boundary of this set. And I'm going to show you some pictures, and then the boundary of the Siegel disk is a subset of that Julia set. So I'm going to show you pictures in a moment. Now, let me just say that one interesting corollary of this. So this sort of finishes the problem I talked about at the beginning for a full measure of rotation numbers. Now, if you choose your rotation number in this class E, but choose it to be unbounded type, so still this class is full measure. And for bounded type, we know that we have a similar theorem, which is easier to prove. And we know that the boundary of the Siegel disk is a quasi-circle. So if you choose your rotation number in this class, but not bounded type, it follows that the boundary of the Siegel disk is a Jordan curve, but not a quasi-circle. So metrically it's complicated, but topologically it's tame. And this, I'm sorry? I'm sorry, I don't hear you.
Why does it follow?
Well, because I said that there is a theorem that for a quadratic polynomial, the boundary of the Siegel disk is a quasi-circle containing the critical point if and only if the rotation number is indeed bounded type. So when your rotation number is unbounded type, but still in this class, you can say that the boundary is Jordan curve, but not a quasi-circle. So I should emphasize, for example, if you look at this picture, I should emphasize that there is an obvious candidate, a sort of topological candidate for the Julia set. Just the combinatorics of the rotation number gives you a topological model for the Julia set. So that's not very interesting. What makes the theorem important is that it actually says that the topological model you have is a realistic model. And the way that topological model is embedded in the plane is actually, after that embedding, you get the actual Julia set. And I should emphasize here that the fact that for almost every rotation number, the boundary of the Siegel disk is a Jordan curve, was announced by Hermann and Yoko 2 years ago. So the theorem, but this theorem gives you an explicit condition on the rotation number. So after I state this theorem, now I can fill in this gap, put this bubble here, and then replace this by D. So now we know what happens in a full measure set of rotation numbers. So the proof is based on topologically, any two locally connected quadratic Julia set with Siegel disk, locally connected quadratic Julia set with Siegel disk, have homeomorphic Julia sets, regardless of dynamics. So topologically, if you forget about dynamics, just look at the Julia set. Any two of these are homeomorphic. Of course, the dynamics is different. The way you sort of interchange these is by the dynamics. But the difference between such a picture and this, although they're homeomorphic, the thing is, here, if you look at the boundary, it's a Jordan curve, but it does not have bound returning in the sense of output. It's not a quasi-circle, but this is very nice quasi-circle. So the proof of, I'm sorry? Yeah, it's not visible. Sorry, I was in a rush to. So the idea is to produce a topological model for the Julia set and for the action on the Julia set. So that's the topological part of the argument. But the most important part is to prove that that's actually the Julia set. So let me explain how. So first, following duad, we consider a synthetic model for the Julia set of a quadratic map with a Siegel disk as follows. So we consider this cubic Blaschke product. This is a rotation z squared, and the Blaschke factor is z minus 3 over 1 minus 3z. So you adjust this number t in such a way that the rotation number of the map restricted to the unit circle becomes theta, anything you want. You can do that. And this is the basic dynamics of this map on the unit circle and its three images. So this is the unit circle. This is the critical point of this map at 1. That's why we chose this parameter to be 3. And you have a double critical point at 1. This component is a pre-image of the unit disk. It maps the unit disk bi-homomorphically. And by symmetry, this symmetric component here maps into the exterior of the unit disk 1 to 1. And then this piece maps 2 to 1 to the unit disk, and therefore this piece maps 2 to 1 onto the exterior of the unit disk. So these two are branched over 0 and infinity, respectively. So when you look at the Julia set of this Blaschke product, you see such a thing, very fuzzy. So all of these figure 8s are pre-images of the unit circle. So you take the unit circle, you take the first pre-image, and then the next pre-images, and then the next pre-images. So you sort of saturate by taking further and further pre-images, and then you take the closure, and you end up with the Julia set. Now, this object itself is not a good candidate for a quadratic map, simply because it has a pole. So this was duad's observation. Okay, so that's a more accurate account of what's happening. So what you do is, on the unit disk, you change the definition of your Blaschke product by performing a topological surgery. So you don't worry about complex structure of anything, because everything is in a topological sense. So you cut out the unit disk, and remember that you had a pole in the unit disk. So you cut it out, but the boundary is a so-called critical circle map. It's a real analytic homeomorphism. So if you look at the restriction of that Blaschke product to the boundary, so if this is T, the unit circle, perhaps it looks like this. It has a critical point. So it's a real analytic homeomorphism which has a critical point, cubic type, at 1. And then there is this now old theorem of Yoko's that these maps are topologically linearizable provided that the rotation number is irrational. There is no real analytic dojo of examples here. So you linearize this map topologically, so you find a basically unique homeomorphism which conjugates the restriction of that Blaschke product here, the restriction of this map to the unit circle, to the rigid rotation by the same angle theta. And then you extend that linearization, because it's a homeomorphism of the circle, you extend it any way you want to a homeomorphism of the disk. And then you replace the dynamics, you keep the dynamics outside as it was, outside the unit disk as it was, and inside the unit disk you conjugate it by the irrational rotation on the disk. So the effect of this is to replace this complicated dynamics inside, which had a pole, for example, here. So you cut this out and glue a topological rotation inside. And on the boundary, by this conjugacy condition, the old dynamics and the new dynamics match. And the effect of this on the Julia set is like trimming all of the interior decorations from these components. And you end up with this. So outside, the dynamics is as before. Inside now, it's a topological rotation. And these are the so-called drops, the pre-images of the unit disk under this new map. So if you consider any drop, for example here, it first maps around for a while, then eventually maps to this component, then eventually maps to this component, but here it's just the topological rotation. Now there's this theorem of Peterson that for every irrational number, when you do this to a Blaschke product, of course this Julia set, or the dynamics, is independent of that extension H you chose, except for the unit disk itself, but that's not important. So this object you get is sort of independent of this H. So no matter what irrational number you choose, when you form this Blaschke product and do this topological surgery on it, what you get is the so-called Blanke-Julia set. This compact set is locally connected and has measure 0. Now, topologically, this looks like a polynomial, a quadratic polynomial, in fact. And topologically, this looks like a Siegel disk. So we would like to take this topological model and somehow conjugate it to an actual quadratic polynomial. So in fact, if you can find an invariant conformal structure for this map, then we can use Alford-Burr's theorem. And when you sort of rectify that conformal structure, what you get by conjugating this map by that rectification must be a quadratic polynomial. Now, this is a big dream, because one reason for this, that we cannot do this for every rational number, is that you have this topological model independent of the arithmetic of theta, but we know that if theta is non-Bruno, then the quadratic polynomial doesn't have a Siegel disk. So obviously, to be able to conjugate this topological picture with an actual quadratic polynomial, you must be very careful about what rotation numbers you choose. So a priori, you know that such a program is doomed to fail if your rotation number is not appropriately chosen. Now the thing is, if that extension H I was talking about here can be chosen to be quasi-conformal, then you can easily construct an invariant Beltrami differential or conformal structure for this map. So here you had some conjugacy on the boundary with the rotation numbers. Then you extended this conjugacy to the disk. Now suppose that this extension is quasi-conformal, can be chosen to be quasi-conformal. Then when you take the zero Beltrami differential, or the standard conformal structure here, which is invariant under rotation, pull it back, you get something here, say sigma, which is now invariant under that modified map F. And then, because all of the pullbacks here, all the branches of F inverse are holomorphic, when you pull it back further to all of these drops, the pre-images, of the unit disk, it doesn't increase the dilatation of this initial sigma, and therefore you can pull the sigma back to all of the pre-images of the unit disk, and then define it to be 0 outside, and what you get is, by the very construction is invariant under this topological action, or now quasi-regular action, and therefore you can rectify it, you do the surgery, and this is actually the way you get this theorem from the Peterson's result, you get this theorem for bounded type rotation numbers. Because of this theorem of Hermann and Schoentek, which says that you can extend this linearization little h to a quasi-conformal map big H if and only if the rotation number is bounded type. This is an immediate consequence of the so-called real f-area bounds for critical circle map. So, the only way you can make this quasi-conformal surgery work by this theorem of Hermann and Schoentek is when your rotation number is bounded type. So, to go beyond bounded type, to prove something beyond bounded type, you have to give up quasi-conformal surgery. There is no way of making this the same strategy work. Right. So, you observe it's so good to have the ID beside you. He gives the more accurate versions of what you say. So what he's referring to is that Hermann proved this theorem using an inequality of Schoentek, which was in a different, perhaps a different context. This is the so-called trust ratio inequality of Schoentek. And Hermann realized that it could be applied in this case. So perhaps it's, I should have said Hermann's theorem with heavy use of Schoentek's idea. So this is the idea. If rotation number fails to be bounded type, this linearization map, which is essentially unique and we have no choice selecting this, is not quasi-symmetric. And therefore, we cannot find an extension which is quasi-conformal, and therefore when you do this, you can't make the surgery work because you don't get anything of bounded rotation. However, the idea is, even if the rotation number is unbounded type, you may be able to control the sort of distortion of this homeomorphism, and therefore the dilatation of this extension. The dilatation may go to infinity as you approach the boundary, so this is not quasi-conformal anymore, but still has nice dilatation properties. The dilatation goes to infinity in a controlled way. And what gives this approach a chance to succeed is this marvelous theorem of d.b, which was not proved in a dynamical context, but it has found some applications in dynamical systems. Peter Osinski proved parabolic surgery using this, and this is another example showing that this theorem could be useful in dynamics. So, following d.b, we say that the Beltrami differential is d.b Beltrami if the area of, so you have a domain and you have a Beltrami form in it. If the size, absolute value of this mu is bounded, then this is ordinary Beltrami differential. But if the area of the set of points where this absolute value is large is exponentially small in that parameter, we call this a d.b Beltrami differential. So this is an exponential condition on the growth of dilatation. And the theorem of d.b says that whenever you have such a Beltrami form on a domain, it's integrable. You can find an absolutely continuous and line homeomorphism such that the Beltrami form of that ACL homeomorphism coincides with this given Bell-Tommy differential almost everywhere. So this is the natural generalization of quasi-conformal maps, and this is the natural generalization of the outsourced third field. I'm sorry. This is the area of the set of points.
X1. I can't see it.
This last one,
Right under the blackboard.
I just want to look alpha over epsilon.
e to the minus alpha over epsilon, for all sufficiently small epsilon. So these homeomorphisms are unique up to post-composition with conformal transformation, just like for the conformal maps. And the important property is that they are absolutely continuous with respect to two-dimensional measures. So area of a set is zero, even only if its image under such map has zero area. But there are some significant differences between these maps and classical quasi-conformal maps. For example, the inverse of the GW map is not GW necessarily. So let me define two.
You may preserve sets of alpha dimension.
I'm very sorry. Could you speak up?
These maps, do these maps present sets of alpha dimension?
I have no idea. In fact, that's one of the questions that I will ask at the end. I don't think anybody has looked at how the house of dimension is transformed under the GW homeomorphism. So that's a very good question, but I imagine it should be hard because the corresponding question for quasi-conformal maps was settled years ago. I don't know. So let's define two sets of irrational numbers. The first set is a set of all irrational numbers such that such linearization, which is essentially a function of theta and unique, has a GW extension to the disk, just to the disk. In other words, we consider a set of angles such as this map has an extension to the disk such that its dilatation, although it goes to infinity, it goes to infinity that way, just restricted to the disk. And the second set, E sub I, is a set of thetas for which this topological model admits an invariant Bell-Tommy differential, just globally. Now, trivially, this second set is a subset of the first set. If you can find an invariant Bell-Tommy, Bell-Tommy differential globally, then when you restrict it to the unit disk, it's W, and therefore that angle, by very definition, satisfies the first condition. However, the main ingredient of the proof, the main idea of the proof is the reverse inclusion. We prove that these two sets are actually equal. And we prove that this set E, set of all angles, theta, such that AN coming from continuous fraction expansion is bounded by exponential of the square root of n is contained in this. So, in other words, this is the strategy of the proof. Every angle with that condition, for every angle with that condition, we prove that this linearization has a GW extension to the disk. And then, by the second inclusion, anything which has a GW extension to disk extends to something on the plane, satisfying GW. Now, the importance of the second inclusion, which proves equality of these two, is that it's independent of the condition of the rotation number. So, anytime you can find a GW extension of this linearization map to the disk, by the equality of these two sets, you're in good shape. You can extend it to a GW structure on the entire plane. So that's an important thing. So in some sense, this equality is strong enough so if somebody else comes up with a stronger condition, proving that for that larger class of rotation numbers, you have GW structure on the unit disk, then by this theorem, automatically you get what you want on the entire plane. Now let me say a word about the proof of these two theorems. So the first theorem is this inclusion, and the second theorem is this inclusion. The idea of the first one is to a large extent due to Yoko's, and Carson and I were very fortunate to have access to this unpublished manuscript, and we realized that what he was doing in that manuscript can be applied to this roundup. So this is the idea. You have some so by lifting to the universal cover of the circle, you can work on the real line. So you have the restriction of the critical circle map, and you have the rotation, which here is just translation. Now you take the backward orbit of this critical point here, and it gives rise to a well-known dynamical partition of the unit interval. Z invariant, translation invariant dynamical partition. So you use the backward orbit of a marked point under the corresponding dynamic, the dynamical system, to find partitions, very fine partitions of the two lines over there. And then you consider for each point in this partition, right here, for each point, so this is, for example, the level n partition, so fix this level. So for each element of this partition, look at this interval and look at this adjacent interval, and take the average and mark the point right above it. And do this same way for the rigid rotation. Now this gives you an actual cell decomposition for, on one hand, for the critical circle map F, and on the other hand for the rigid rotation. So this is the picture of that cell decomposition of the upper half plane for the rigid rotation. So these are cells of level n, and these are cells of level n plus 1, and so on. So as you approach the boundary, because the size of that partition, as you increase the level, the mesh of that partition goes to 0 exponentially fast. The size of these cells shrink exponentially fast. And using the real a priori bounds for the critical circle map, you can show that these cells have bounded geometry. So they pretty much look like squares. So if I can find, and these two cell decompositions are combinatorially equivalent. So I can take each cell and map it, the boundary of each cell, and map it to the boundary of the corresponding cell piecewise affinely. So I take a cell in the first decomposition for the critical circle map the boundary affinely, piecewise affinely to the boundary of the corresponding cell in the second decomposition. Now there's a big difference between the cells in these two worlds. The cells in the linear world on the left have a very nice lower edge, so that these points which belong to the upper edge of the next level are more or less equally distributed. So these lengths are more or less comparable, no matter how many of them you have. And the number of these lower points on on the lower edge of each cell basically is determined by AN, which comes from the rotation number. On the other hand, for the critical circle map, this is the fundamental estimate of Yoko's. These points are not equally distributed. The length of these intervals basically shrink like 1 over n squared. Because this is the perturbation of the parabolic Mobius transformation. So here you have, when theta is not bounded time, AN could get arbitrarily large. But if AN gets large in a controlled way, then we can show that there is a quasi-conformal extension of this map on the boundary to the interior of each cell, which has a controlled dilatation. So what you do, first you normalize these cells, map them to squares without changing the relative distances, the sort of horizontal distances between the points. So these points for the translation of rigid rotation are equally distributed, more or less, and these points shrink like 1 over n squared from each side. And then you normalize it further by mapping to the upper half plane. So up to a quasi-conformal change of coordinate, the problem can be reduced to this. Now, look at this picture first. This picture like this picture is invariant under a power of your critical circle map. And it looks like the fundamental domain of a Mobius transformation with a parabolic fixed point almost at the center. This is what's given by your opposing equality. Now, if I can find some nice transformation, it sort of spreads them apart, make these points more or less equidistributed, then I can map that configuration to this configuration by a quasi-conformal map whose dilatation is independent of my choice, some universal dilatation. So up to a quasi-conformal change of coordinate, right? Up to a quasi-conformal homeomorphism, the problem is reduced to this. Instead of working with a map which, on the boundary, which maps this configuration to that configuration piecewise affinely, we can replace it by a map which maps this configuration to something in a piecewise Mobius fashion. So up to a quasi-conformal change of coordinate, we have this problem. We have a map, so this is the upper half plane. We have finite number of points in the upper half plane. And suppose that we have an action on the boundary, say H, which is piecewise Mobius, and these are the fixed points of that Mobius transformation. So you have a Mobius transformation here, and this is the fixed point, repelling fixed point, attracting fixed point, say a Mobius transformation here, and here, and so on. And suppose that the multipliers here, the repelling multipliers are say lambda 1, lambda 2, and so on. All bigger than 1 is real, in fact. Now, so we would like to show that, actually this follows from the construction of Siegel, that in this case, whenever you have a piecewise Mobius transformation on the real line, you can extend that piecewise Mobius transformation to a quasi-conformal homeomorphism of the upper half plane whose dilatation is dominated, can be estimated in terms of the largest logarithm of the largest multiplier here. And the proof is extremely simple. So all you have to do is to consider this hyperbolically convex set. Extend your map to the identity here. And then on each topological disk here, you have some Mobius transformation. You can interpolate between this Mobius transformation to the identity map. It's a very simple problem in quasi-conformal maps. If you want to look at it the other way around, this is conformally equivalent to the strip. You have the identity here, for example, and say z goes to z plus something here, the positive. So you have a translation here, and you have identity here, and you want to find the best quasi-conformal interpolation between these two with the least dilatation possible, and it follows that the least dilatation possible is given by the logarithm. So in terms of that picture, if this multiplier is, say, lambda j, this is logarithm of lambda j, and the best dilatation is, say, 2 times 1 plus logarithm of lambda j squared. In this case. So first you solve the problem here. This is the best you can do, interpolating between the identity and the rigid translation. And then this is conformally equivalent to this. So when this is Mobius, this is like the translation here. We can interpolate between this Mobius transformation and the identity here as well, getting the point of infinity, and then you extend it to the identity of that convex set. So in our case, it follows that to spread these points apart, you have n of them at level n. To spread them apart, almost equidistributed, you need to apply a Mobius transformation whose multiplier is comparable to an. So the multiplier should be comparable to an in order to spread these points apart, make them almost equidistributed. Therefore, if you choose your rotation number in that class E, by the definition of E, 1 plus log an squared is dominated by n, basically. It grows linearly by the definition of the class E. because AN is comparable to lambda, it follows that in that case, the extension to a cell of level n, you can find an extension to the cells of between the cells of level n in a quasi-conformal way, whose dilatation, real dilatation, is comparable to n, at most comparable to n, on a set whose area is exponentially small in n, because the area of the cells of level n is exponentially small in n. And that's exactly the GW condition. Now, the second part is much more difficult. This is the main difficulty in proving the theorem. So let me give you an outline of the proof of the fact that whenever you have a GW structure on the unit disk, by pulling back, you get a GW structure on the plane. Now, this is the fundamental difficulty. The fundamental entity here is the recurrence of the critical point. When you have the quasi-conformal map and you pull it, the quasi-conformal map, a Beltrami differential of bounded dilatation, and you keep pulling it back by a conformal map, you don't change the dilatation. You may change the area. You may have a lot of area distortion, but because the dilatation doesn't change, you're in good shape. What you get has bounded dilatation. Now, it follows that in this case, even when your rotation number is bounded type, you have a large amount of area distortion. So when you start with the unit disk, what you want to do is, so you have a whole bunch of so-called drops, which are pre-images of this unit disk. So you have a GW structure on the unit disk. This means that the region which with large dilatation is concentrated on a very tiny annulus whose thickness is exponentially small. But when you keep pulling it back, it is a conformal map, but you have to control the area of the pre-images of this kind. And when you keep pulling it back, what happens is that after a large number of pullbacks, when you're, say, here, you see that this red region, well, what you see is green, but just pretend it's red. This red region, which was exponentially small in area comparable to the unit disk, becomes huge. In this disk, almost everything will be red because of this huge amount of area distortion. And this is not a hypothetical enemy. This is a real enemy, because if you look at this, I mean, this is not because we cannot control area distortion, therefore it may happen. It will happen. And this is the picture. This is red. So you start with a very tiny annulus in the unit disk, and when you pull it back, you see large areas, red areas here. Now, if you detach from the post-critical set, which is the unit disk, then you're in good shape, because the area distortion will be bounded after. As soon as you go away from the unit circle, then you're in good shape. All the other pullbacks are good. But when you keep pulling it back, along the drops, whose roots are on the unit circle, if you zoom in and magnify one of these drops, which are extremely close to this one, but have their roots on the unit on the unit circle here, this means that you start with this, and you kept taking pullbacks for 1 million times, and by the time you're here, almost everything will be red. And that will happen, independent of the rotation number. What saves you in the bounded time case is that you don't worry about the area dispersion, because everything has bounded rotation. So this is the most annoying difficulty in this problem, and the way we dealt with it was by constructing a Borel measure on the unit disk, which is exactly what you want. What you do is you define a measure on the unit disk So you take the subset E of the unit disk, you compute its area, plus you push forward a Lebesgue measure from all of the drops to this unit disk. So you take a Lebesgue measure on each drop, which is a pre-image of the unit disk, push it forward like conformal branch. It maps conformally into the unit disk. So push it forward, you get some measure on the unit disk. You add them up. And the total measure is bounded by the area of the filled Julia set, which is universally bounded, so that's okay. So we look at this measure. This measure is obviously absolutely continuous with respect to the Lebesgue measure. If you take a set of measure 0, then pull back at measure 0. So we know that so we have this measure nu, and we have area. So we know this relation, and therefore, as area of something goes to 0, we know that nu of that thing must go to 0, but remarkably, we can find some universal estimate on how fast this measure goes to 0. This is basically bounded by constant times a universal power of the area. So this may depend on theta. And this is universal. It's independent of everything. So once you prove this fundamental inequality, this is exactly what you need to prove that the pullback of the Gita V structure on the disk is Gita V on the plane. Because if area of something on the unit disk is exponentially small, this says that its nu is exponentially small, perhaps with a different exponent, but nu is exactly what you want, because nu measures the area of that original set, red annulus, plus all of its pre-images. Now the proof of this fundamental inequality or estimate is complicated. It's based on a lot of I don't think there is a fancy shortcut for proving this. So you have to work at the geometry of the so-called puzzle pieces in this model. So you have to completely understand how the so-called puzzle pieces in this model behave under taking pullbacks. And then the idea of the proof of this of that inequality is, so let me just read for you this last few lines. So the idea is that you cover this so-called red zone by a union of puzzle pieces. These are closed topological disks which are dynamically defined. So you sort of cover those this thing with a dynamically defined annulus rather than an arbitrary annulus. And those are sets that, so when you look at it, so the first puzzle piece looks like this in that model. This is the first puzzle piece, which is bounded by two rays landing at these two fixed points and potential. So we take this beta, this is the first puzzle piece, and then you keep pulling it back, and this sort of covers, it gives you a nice covering, dynamically defined covering for the filled Julia set, and then you prove that the area of the nth level puzzle pieces decrease exponentially fast in n, and that's the fundamental estimate that allows you to prove this theorem, that the natural measure of the unit disk is bounded by an exponent of the Lebesgue measure. Oh, this is hand. This is made by hand. No, this is not computer. Actually, it's not made by hand. It's made by computer. But it's X-bit. question. The thing is, I don't think, he's asking if I understood your question correctly, if you can sort of forget about the dynamics and find it. So having the circle homeomorphism, find the Gita beam structure just using the properties of the circle. You can do that, but you end up with a much worse condition of data. So this is a very good question. And I would like to ask everyone who's interested in quasi-conformal theory to try to prove, to develop a Berling-Alfors theory for W homeomorphism. We know that the circle homeomorphism is quasi-symmetric if and only if it has a quasi-conformal extension to this. However, it's not known, at least I don't know of any such data, a necessary and sufficient condition for a circle map to have, the circle homeomorphism to have a W extension on the disk. You can find some sufficient condition on a circle map to give you a W extension, but those are not good. The fact that we can come up with such a nice, strong, full measure condition is because we really use the dynamics. But it's a very natural question, and I guess a very important problem to have a Berling-Alfors theory for W homeomorphism. That's what we're going to do.
Any other questions?
Your picture suggests that when you take the Siegel disk and inverse images in the union and closure, then in your case you get students.
Right, right.
Now, is this property equivalent to local?
Well, definitely, local connectivity implies that property. Let me see here. Not just the critical circle maps coming from this flush device. Yeah, any critical circle map whose rotation number is class E, then it has to be Oh. Well, offhand, I definitely Bruno. Yeah, it's conceivable that that's what Bruno was hiding the veil.
I don't know whether this question was asked, I couldn't hear what was said, but do you have any conjecture on which class would be the optimal class for your theorem to hold?
I do have some conjectures, but I'm not going to tell you because it's very dangerous making conjectures.
Would you think it's true for Diophantine numbers?
I'm sorry?
Would you think it's true for all Diophantine numbers? Or?
Well, it's generally believed that every Diophantine is locally connected. I don't know about measure 0, but as I said, I mean, you can make conjectures, but it's very hard to say.
The next talk is in 10 minutes.